Hello, everybody. So, I hope you're doing well. And so, let's start with this video. And today, we will conclude the topic of laser cooling. So, I'll remind you that in the last lecture, we reviewed quite in detail the physics of subdoppler cooling, and also with some numerical simulations at the end. And I will start by resuming the result of those simulations to explain a kind of some general features of a subdoppler force. Then we will see with some qualitative arguments what the limits for the subdoppler temperatures are, and then we will see what is the ultimate limit for laser cooling. And we will also discuss some experimental implementation. So, without spending too much time on this introduction, let's go straight into the last part of explanation of subdoppler cooling, and let's see what is an order of magnitude for the subdoppler cooling force. Let's see it. In the last video, I've tried to convince you of the efficiency of a subdoppler cooling mechanism that relies on these optical pumping events that, in average, lead to a reduction of mechanical energy. And this is due to a combination of optical pumping with a loss of kinetic energy that arises when the particle climbs the potential hills that are produced by the optical dipole force. And so, to convince you of that, I show you the results of this numerical simulation. And here you can see that as a function of time, so the velocity is reduced, and so you have a force. And you can see here the character of these forces. This is just a numerical experiment, and you see here that at least for small velocities, you have a kind of friction force that is similar to what you had in Doppler cooling. The main difference is the slope of this force that is much higher in the case of subdoppler cooling with respect to the Doppler theory. And I would like to give you a kind of semi-analytical argument for that today. That will be useful to understand what limits for temperatures are. So, in order to do that, we can, let me now erase that, and let me take the figure that we use for explaining subdoppler cooling. Here it is. And let me also remind you what the shape of a force as a function of velocity was in Doppler cooling. So when we discussed the theory of Doppler cooling, we demonstrated that the force that you have as a function of velocity has this kind of character. So F as a function of V, it is something like this. And I also remind you that the maximum of this force was for a velocity that we called a capture velocity, Vc. This is minus Vc. And we have seen that this capture velocity in the Doppler theory can be written as the absolute value of the tuning divided by the laser wave vector k. And we've also seen that for the parameter regime in which Doppler cooling works in the optimal way, so this detuning is on the order of gamma. So in particular, we have considered gamma half as the minimum of the Doppler temperature, and so for the rest of this discussion, we can consider as the capture velocity for Doppler cooling the velocity corresponding to the best performances of Doppler cooling. So this is the capture velocity, gamma divided by 2k. And let me indicate that this curve here is for the Doppler cooling theory in the best situation, for the best parameters. And another quantity that we had introduced is the friction coefficient that basically describes the steepness of a linear part at small velocity. So this is a damping coefficient or friction coefficient. And again, in the case of optimal detuning, this was on the order of h bar k squared times S, where S is the saturation parameter. Then there was a prefactor of order 1, but we don't care about that. Okay, so these are the numbers, the parameters in the case of a Doppler theory. So let me stress here that this is for Doppler theory, because now we'd like to see what these parameters are for the subdoppler case. And I also conclude this list of parameters, of course, writing what is the temperature limit in Doppler theory. And the minimum temperature achievable was given by h bar gamma divided by 2. So this is the Kb Doppler temperature. Again, for the optimal choice of laser detuning. Okay, so let me write explicitly that these parameters now are for the Doppler, cooling. So let's try now to evaluate these quantities in the case of subdoppler cooling. And so let's refer again to the scheme of Sisyphus cooling that I have on top of my head. And let's start with the capture velocity. So the capture velocity, we define that in this very simple way as the velocity that corresponds to the maximum of a force. As you can see that from the plot. So we have to evaluate the velocity of the atom that provides the most efficient subdoppler cooling mechanism. But this is kind of easy to understand. So when we introduce the idea of Sisyphus cooling, we refer to this ideal situation in which the atom basically moved by a distance lambda over 4 before absorbing a photon and before being pumped to the other internal state. And then we assume that, so after this loss of energy, it could move by another distance lambda over 4 before a new absorption spontaneous emission event, and so on. So basically, this is the luckiest situation. So the luckiest situation is that corresponding to a distance lambda over 4 between different absorption and spontaneous emission events. Because in this way, so the atom can lose the maximum of potential energy with a maximum probability of optical pumping to the other state, and so this is the best we can get. So let's evaluate what this velocity is. This optimal velocity corresponds to a travel distance of lambda divided by 4 in a time that is 1 inverse of absorption time, absorption rate gamma A that we defined in the last lecture. So let me write basically this as now gamma A divided by K. So again, we are interested in orders of magnitude here. So instead of writing all the 2 pi factors and these 4 factors, so lambda is 2 pi divided by k, and so 2 pi divided by 4 we approximate with 1, and so we can get this capture velocity, subdoppler capture velocity as gamma A divided by k. And last time I gave you the expression for gamma A, and so I will recall the expression now in the limit in which we are interested in, saturation parameter S much less than 1, and detuning much larger than the transition line width gamma. In this limit, gamma A, so the absorption rate of photons, can be written as basically gamma divided by 2, and then we had S, the saturation parameter, times gamma divided by 2 delta square. And we also have a K at the denominator. So this is the capture velocity for subdoppler cooling. And so you can see here that this capture velocity is much smaller than the capture velocity for Doppler cooling. And it's easy to see that because I just need to recognize that in this expression we have the capture velocity for Doppler cooling already there, because this is gamma divided by 2k. So this is what we defined as VCD. So this is the Doppler capture velocity times S times gamma divided by 2 delta square. But now both this quantity is much less than 1, and this quantity is also much less than 1 because of these assumptions. And so this capture velocity in the subdoppler cooling regime is much less than the best Doppler capture velocity. So this is much less than VC Doppler. Okay, so let me take this result and put it here below to express so we can compare with the Doppler case. So we have VC subdoppler equal to, and I will copy this result. Okay, good. This is for the subdoppler cooling case. So if I plot it on this graph, subdoppler, we will have here some capture velocity for the subdoppler cooling case. Good. Now we want to have an estimate of a slope, so of a friction coefficient in the subdoppler cooling case. So in order to do that, we can estimate the force. And we will estimate the force in this particular configuration. So in this, for a velocity of the atom that corresponds to the maximum force. So in this situation that is depicted in the scheme here, what is the force that the atom experiences? I need to free some space, and so I will move it below and then I will move it up again. Sorry for the need of reshuffling things in the screen. So this force will be given by what? So this force, we have said, that comes from the optical dipole force. The optical dipole force is a conservative force, and we can write it in terms of a gradient of the optical dipole potential. And so this can be written basically as delta E divided by lambda over 4. What is delta E? So delta E is the energy lost in one of these processes of absorption and optical pumping to the other state. So if I look at the scheme here, so delta E is this quantity. And we are losing this delta E on length scale of lambda divided by 4, and so energy divided by a distance, so this is the force. So again, let me write it and let me approximate that again. So what is delta E? Delta E is, for this particular choice of the quantum number, so delta E is 2/3 of maximum light shift, so that we called U0, divided by lambda over 4. And so again, let me write these as basically k times U0. So we have all these factors that are on the order of 1 that we can simplify. Good. So now we can write the expression for the light shift, for the optical dipole potential, that we know is, at least in this large detuning limit, we can write it as a h bar omega square divided by 4 delta. So now I have to manipulate this expression a little bit, because we want to extract the friction coefficient out of this expression of force, and so I need to have some velocity dependence there. And so in particular we can, so this is the maximum value of a force, this maximum value for the force is obtained when the velocity is corresponding to the capture velocity. So let's make the capture velocity appear in this expression. And we can use the expression that we have at the bottom of the screen. So basically that tells you that the VC subdoppler is equal to VC Doppler, so gamma divided by 2k, times S times gamma divided by 2 delta square. So the same expression we have written before. And so this is gamma to the third divided by 8k delta to the second power times S. So this means also that, of course, VC subdoppler, and now let me write in this way, times 8k delta square divided by S gamma cube is equal to 1. So basically I took this expression, just divided for what you have at the right hand side of the equation to get this quantity. And so if this quantity is equal to 1, I can just take that and multiply the expression above by this quantity that is equal to 1, and I will have the same result. That's a bit of a trick, but now we see why we do that, because basically we can recognize that all these expressions that we will simplify in a moment takes the meaning of a friction coefficient, because this multiplies the velocity. So we can write this as the friction coefficient in subdoppler cooling times the capture velocity in subdoppler cooling. Okay, so let me now erase these and write that alpha subdoppler, so this friction coefficient, and we will make some simplifications now, of course, can be written the following way. So we have 8 and 4, that makes 2. Then we have omega square. Then we have, I'll take gamma square and write it here for reasons that will be clear in a moment. Then I have S. Then I have k square, h bar, so k square, h bar. We have delta, so delta square divided by delta makes delta, divided by gamma. That's all, because only VC subdoppler has been left. And now we can simplify this expression further, because we recognize now that this quantity, 2 omega square divided by gamma square, is nothing but the saturation parameter S. So we can just simplify this, and we are left with h bar, k square times delta divided by gamma. So, as a first thing, let me put some order here and take this result and put it in this table that we started to fill. Done. Now, this expression is particularly interesting because we see that this subdoppler friction coefficient can be expressed in terms of a Doppler friction coefficient. So, and what you get is, of course, h bar k square. So it is already in the expression for the Doppler friction coefficient. So we miss an S factor, and so at the end we can rewrite this expression as, so h bar k square is alpha Doppler divided by S, and so this will be alpha Doppler times delta divided by gamma divided by S. And of course, let's consider what happens in the interesting parameter limit, in which S is small, delta is large, and so delta large, S small, means that both these quantities are go in the same direction to make this friction coefficient much larger than the Doppler friction coefficient. So this quantity is much larger than alpha Doppler. So what do we see? And so let's use these results to make a kind of update of a plot above to include the effect of subdoppler cooling. So subdoppler cooling, you see that is a mechanism that operates on a narrow region of velocities, because the subdoppler cooling velocity is very small, but the force that you can get has a much higher friction coefficient. So basically, we can think to a modification of Doppler of a Doppler cooling force in this way. So in this range of velocities, you have a much steeper curve here. So something like this. And so you might think that here you will have some kind of features like this. So this is really very qualitative, but just to express this idea that we also find in, for example, numerical simulations of this force, and this is indeed what we are observing. And so let me take that numerical example again now, and you can see basically that these characters are already in the simulation. So you have a higher steepness, but on a smaller velocity range. So the Doppler capture velocity is, in this graph, is out of scale, so it is much higher than the subdoppler capture velocity. But the steepness is already evident that in the case of the subdoppler mechanism is much higher. So, because of this extra cooling mechanism, so this is how your force looks like. And so at the end, of course, this higher friction will lead to an increased efficiency of the process, so a lower temperature. Now, of course, we have to complete this table, putting the value for the subdoppler temperature. And actually, the calculation is not as easy as what we did in the case of Doppler theory. So I will not repeat that. Now, as in the case of a Doppler theory, you expect that this kind of cooling process will arrive to some steady state, and this steady state distribution of velocities will be connected to kinetic temperature, subdoppler temperature, and this value will be determined by the balance between two effects. So a cooling effect that is associated to the mean value of force, so to what we have plotted in this graph, and to the fluctuations of a force that will cause dissipation, and so a heating process. And so from the balance between the heating and the cooling effect, we could derive a subdoppler temperature. And this subdoppler temperature will be given in complete analogy with what we have studied in the case of a Doppler theory by the ratio of a subdoppler coefficient, diffusion coefficient, to a subdoppler friction coefficient. Now, I will not derive the diffusion coefficient in subdoppler cooling because it is rather complicated. And the reason is that it also involves the fluctuations of a dipole force that we never talked about. But you also have fluctuations of dipole force in the same way that you have fluctuations for the radiation pressure. So what we can do, just to, you can believe that, and so it can be demonstrated that this diffusion coefficient is on the same order of what we had in the case of Doppler cooling. So now, of course, you can write this as the Doppler diffusion coefficient divided by the Doppler friction coefficient times the ratio of alpha d to alpha st. And so this is, first term, you have the Doppler temperature, kBTD, and then you have the ratio of the two friction coefficients. But this ratio, we have already calculated that, and it is given by this expression. And so this is kind of intuitive to understand, at least if you consider the dissipation term to be the same. If you have a higher friction, so the cooling is more efficient, so in the unit of time, your subdoppler force can can remove energy faster than the Doppler force, and so the temperature you expect to achieve is a lower, will have a lower value. So this ratio is S times gamma divided by delta. But again, in the parameter regime you are working in, so S is a small quantity, so this is much less than 1, and this is also much less than 1 because the tuning is large, and so this temperature is much lower than the Doppler temperature. Good. And let me now rewrite this expression. So I will clean now this last line to have a compact set of useful quantities. Good. Let me now show you one last thing, is let me make explicit this last expression on the subdoppler temperature. Because there is another picture for understanding this temperature limit. And it is the following. So Kb, I will write it here. Temperature subdoppler is Kb Doppler temperature, that is h bar gamma divided by 2 times S times gamma divided by delta. I just substituted the expression for kBTD. Okay, now let me express the saturation parameter in terms of Rabi frequency. And so S can be written as 2 times the square of Rabi frequency divided by the square of gamma. Now you see that you can simplify gamma out of equation. Also the factor 2 goes away, and so you find h bar omega square divided by delta. And let's remind that these are just orders of magnitude. So I don't pretend these numbers to be exact. So just some estimates of the orders of magnitude. And so you can see here that this subdoppler temperature, basically you recognize that h bar omega square divided by delta is basically a part factor on the order of 1. This is the light shift. So this is what we have indicated as U0 in the plot above. And this is also an argument that you can find in books quite often. So in very simple terms, people say that the limit for subdoppler cooling is basically set by the energy scale of light shift. So basically this cooling process is efficient only when the atom basically has the possibility to climb the potential hill and so arrive from the bottom to the top of the hill. And so this corresponds to an average energy that is on the order of the height of a hill, that is basically on the order of U0. So this is an argument that you can find quite often. I'm not completely happy with this argument because there is much more. So you can have cooling, and we've seen that from the simulations that I gave you last time, also for smaller energies than the depth of a potential hill. But anyway, this at least gives the right scaling. So this is the relevant energy scale that we have to compare with, and so it makes sense that we have this light shift energy scale in the final subdoppler temperature. And so what do you see now? You see that this subdoppler temperature depends on the parameters that you choose. Differently from the Doppler temperature that had a minimum, and I plotted here just a minimum value for this temperature that depends only on gamma, on the transition line width. Now you see that this subdoppler temperature depends on two parameters. Depends on the intensity, and in particular, the lower is the intensity, the better the temperature is, the lower the temperature is. So this is why we are working in this regime of small intensity. And also, large detuning helps, because this temperature gets lower when increased with detuning. And this is why I told you that it is helpful to work in this regime of large delta. And so it seems that from these expressions, it seems that you don't have a lower limit for the subdoppler temperature. It seems that you increase your detuning, so you decrease the saturation parameter. So low intensity, large detuning, that means that these potential hills will be very small, and so the energy scale for the process will be smaller and smaller, so you can get lower and lower temperatures. And of course, this is not true. But it is true that, for example, increasing the detuning helps. And we already know that. And so let me now take, again, the slide of the first measurement of subdoppler temperatures. That's it. So remember this figure. So this was the first measurement of subdoppler temperatures that were clearly violating the Doppler prediction. And if you look at the experimental points, so you see very clearly that things get better when the detuning is made bigger. So you can get a lower and lower temperature as the detuning is increased. And this, at least at a qualitative level, is in agreement with our prediction that the subdoppler temperature is decreasing as 1 over delta. And of course, we cannot tell if this is really 1 over delta or 1 over delta to some power or to some exponential function and so on. And also, let me tell you that the line that you see in this plot is not a fit to the data. And it is not a fit because basically there was no theory to compare with. So the only model that was available at that time was the Doppler theory. So the theory of Sisyphus cooling only arrived a few years later. And so basically this is why in this paper, so these measurements were not tested against any theory. So the theory only arrived later. So you can see here this, at least at a qualitative level, so the agreement with general principle of subdoppler cooling works. And let me only tell you one point. So if we look at the data, so it might you might see or you might not see that maybe there could be some kind of limiting behavior here. So it seems that the data seems to approach some kind of finite temperature. At some point, increasing the detuning does not really help. And of course, this is an experiment and there might be experimental issues, a myriad of possible imperfections or effects that one should control very carefully, especially when you approach this limit of very low temperatures. We will comment on some of these points in one of the next lectures. And of course, the theoretical expectation does not predict this kind of behavior because it predicts better and better temperature as delta is increased. So let me just tell you that in the very last part of this lecture, we will see that at some point some of the very first approximations that we made when we started discussing about laser cooling already several lectures ago, at some point will start to fail. And so we will discuss these in the next video in connection with what we call the recoil temperature limit for laser cooling. That is not what you see here. So this will be much lower, but let me just tell you that at some point there will be another limit that for which this prediction will at some point will have to fail because of a failure of approximations that we made. Okay, we'll discuss it later. Good. So subdoppler cooling is over. We've spent a lot of time on it because it is a nice piece of physics, of atomic physics. Let me close this video with another topic that is connected in some sense to subdoppler cooling because it is connected to real-world atoms. And this will be a very experimental discussion. So, the question is the following. If I have a real atom, rubidium, sodium, or potassium, or whatever, what is the best transition that I need to use for laser cooling? So let's discuss that, and let me take the spectrum and the energy levels of a real atom. And I will not consider sodium in this example, I will consider rubidium. So let's see it. So this is the level structure of an alkali atom as rubidium-87. That we already reviewed in the first lecture, and so you have the D1 and D2 lines. For rubidium, the wavelengths are 780 nanometers and 795 nanometers, and the line width is about 6 megahertz for both the transitions. And for both the transitions, you have a hyperfine structure, because you have a hyperfine splitting both in the ground state and in the excited states. So the hyperfine splitting in the excited states is much lower than what you have in the ground state. So in the ground state, the splitting is about 6 gigahertz. So in the excited states, it is on the order of hundreds of megahertz. So it's not a two-level system. And you can excite many different hyperfine components of the two fine structure lines. So let me draw all the possible transitions you can excite. First, you have two different possible starting points. You have f equal 1 and you have f equal 2. And let's start with f equal 1, so the lower hyperfine state. And so let's see all the transitions that one can induce that are compatible with the selection rules. Selection rules that, of course, tells us that delta f should be 0 or plus minus 1. So first choice is the excitation of the D1 transition from f equal 1 to f prime equal 1. Or we can have, of course, also the transition from f equal 1 to f prime equal 2. Then we can excite instead on the D2 line, and so there we can have a transition from f equal 1 to f equal 0, that is allowed by selection rules, or a transition from f equal 1 to f prime equal 1, or a transition from f equal 1 to f prime equal 2. We cannot have this transition. This transition is forbidden by selection rules because this would be a transition with delta F equal 2. That is not allowed in electric dipole transition. So this is not possible. So we have these 5 transitions from an atom in the F equal 1 state. Then there could be other choices if we consider the upper hyperfine state. Because we know that we already reviewed that typically if you consider a a gas of rubidium in thermal equilibrium, you will have population of both this state and this state. So both will be good choices. So we'll find atoms in both states. So we can also think of a transition for laser cooling that starts from the upper hyperfine state. That is a kind of metastable state with a huge lifetime. So the first possibility is a transition from f equal 2 to f prime equal 1 on the d1 line, or f equal 2 to f prime equal 2. Then, going to the d2 line, okay, we cannot have this, right? So we cannot have 2 to 0 because of selection rule that I've written above. So let's erase that, and let's consider the transition from 2 to 1. Then the transition from 2 to 2, and the transition from 2 to 3. So 5 more possible choices. So now you have to decide. So you have to decide which of these transitions is better, if there is a better transition than others. Now, the answer is that only one can be used. And why is it that? Because basically, when you perform laser cooling, and we have already introduced this idea, you need a closed transition. And so we have already seen that transitions with delta F equal 1 are good choices because transition with delta F equal 1, so transition which connect one state to a state with a higher value of F, are generally speaking closed transitions for every possible choice of the polarization of light. So we want to play with a transition with delta F equal 1. And we want a closed transition, I say it again, because in a closed transition there are no dark states. And so the atom can scatter as many photons as you want. And we need a lot of photons to be scattered in laser cooling. So we don't want dark states for laser cooling. So let me write explicitly, closed transition, no dark states. So we can remove all the transitions which do not satisfy this selection rule. And so let me see. So the first transition is, no, we have to throw it away because this is 1 to 1. Then we have 1 to 2. 1 to 2 is okay. Then we have 1 to 0. No, it is bad, so this is open. And also 1 to 1 is open, so we cannot use that. 1 to 2 is okay. Then, transitions starting from the F equal 2 state. So the first one is the 2 to 1, which is not good. Then we have 2 to 2, which is not good. Then we have 2 to 0, that is not good either. 2 to 2, that is not good. 2 to 3 is good. So if we apply this criterion of choosing a closed transition, so you see that we are left with only 3 choices. 2 transitions start from the lowest hyperfine state, 1 transition starts from the upper hyperfine state. So you have 3 possible transitions, but again, only one will win. The reason is the following. So this criterion for the closed transition, so for the absence of dark states, basically only refers to the Zeeman structure, to the magnetic structure of the atom. So let me write it explicitly that this condition will refer to a closed transition, so absence of dark states, when we consider optical pumping between different MF levels. So inside, so within the hyperfine manifold. But then we can have a different form of optical pumping. And let's consider what happens on the two transitions that start from f equal 1. So let's consider the first transition. So if an atom is excited from this state to this state, then in the decay, so in the spontaneous emission that follows the absorption, so this atom can, of course, go back to the initial f equal 1 state. But because of selection rules, it can also decay to the f equal 2 state. And so this is bad, because this means that your laser will not be resonant anymore with atoms that have decayed to the upper hyperfine levels. So the reason is simple, because the transition line width is so small with respect to the hyperfine splitting in the lowest, the ground state, that basically your laser, your cooling laser, will be not resonant with atoms in the f equal 2 state anymore. And so at the end, so basically you will pump all your population in the f equal 2 state, and so you will not have any more atoms in the f equal 1 state. So everything will be pumped in the f equal 2 state, and so you're fucked, basically. So all the population is there, stays there. So this is a kind of optical pumping, but this does not happen in the hyperfine manifold. It happens between different f states. So again, this is bad. So this is a kind of dark state in a kind of optical pumping process that you have between different f levels. Okay, so we don't want this bad thing to happen. So let's remove all these. Okay, I also removed the second transition because it was connecting the same states, f equal 1 to f prime equal 2, only on the D2 line. And so you see now that only one is left. Luckily, only one is left. But this transition is good. Why? Because it is a close transition if we consider optical pumping within the hyperfine manifold. But also, since the upper state is a f prime equal 3 state, so from f prime equal 3, so the atom can decay only to f equal 2. So it cannot decay to f equal 1 because this would violate selection rules, because this would be a delta f equal 2 transition. So this transition is good. So 1 out of 10 possible choices is good for laser cooling. And so this is also why I considered, when I introduced the topic of optical pumping, I was referring to this situation of a transition from f equal 2 to f prime equal 3. That is what you have in rubidium, but you also have the same with sodium and with other alkali atoms. Okay, a really very last point, and then we conclude this video. Also, this transition has problems. Even this transition has dark states. Why? So there is no apparent reason for that. So why it should be like that? So I plotted here all the energy levels up to the 2p3 state of rubidium. So there are no other intermediate levels where the atom can decay that can provide some branching ratio to some dark states. And we have taken into account selection rules properly. So it seems that really an atom in the f prime equal 3 state cannot decay to other dark states. You can have a dark state because when you excite your transition from f equal 2 to f prime equal 3, and you need to use a proper laser with a proper frequency to excite this transition, anyway, you will always have some probability of non-resonant excitation to other levels. So we just consider the resonant process here. But then you have non-resonant processes. For example, the closest non-resonant process is the excitation, unwanted excitation, of the atom to the F prime equal 2 state. So this is the closer state that is coupled to the ground state that will be excited, of course, in a non-resonant way, because your laser will be somewhere here. So I've drawn this dashed line because we know, of course, that if you want to perform laser cooling, you need to have red detuning. And let's consider Doppler cooling, for example. And let me indicate this detuning as delta 3. And let me consider delta 3 in absolute value. This delta 3, in the optimal case, will be gamma divided by 2. So gamma is 6 megahertz, so we can consider typical detuning on the order of 3 megahertz with respect to the transition. But then you will have some detuning delta 2 that is not wanted, but it is there, from the state that is right below. And this detuning, let me write it, is 2 pi times, basically, so this is 266, and so this will be 263, 264 megahertz. Okay, you would say, yes, it is, of course, 2 orders of magnitude less than the transition we are interested in. So you might think that this would affect your atom just in a minor way. So the probability will be very small. Let's evaluate this probability. So we know that probability of absorption is a Lorentzian, as a Lorentzian line shape. And so we can write the number of let me consider probabilities. The probabilities of the process of excitation to the F prime equal 3 state. So let me write in this way. So P F prime equal 3. That will be basically given by 1 over 1 plus. We know that we have 2 delta divided by gamma square in the Lorentzian function, with some prefactor that I don't care because I only want to need the dependence on the detuning. And so if we choose, as in this case, delta equal to gamma half, so this will be 1/2, just this factor. So this, of course, is order of 1 because the light is near resonant. So if we consider the probability to excite the F prime equal 2 state, of course this is much less, because of course this is, so this was delta 3, now we have delta 2. So this 1 plus 2 delta 2 divided by gamma square. So basically, what do we have here? So we have delta 2 is 260, so but we can even take 300 just to make calculation simpler. So the 1 can be neglected. So this would be gamma divided 2 delta 2 square. So this will be 6 megahertz divided by something on the order of 600 megahertz square. So this probability is 10 to the minus 4. So in average, one atom every 10 to the 4 will be excited to this F prime equal 2 state. But then this atom will be basically lost with high probability, because from this state now, so this transition that is an open transition, for example, this atom from this state can decay to the F equal 1 state, and so this atom will be lost from the laser cooling cycle. So we don't want this process to happen. But you might see, of course, just probability of 10 to minus 4, who cares? But remember, when we perform laser cooling, we want a lot of photons to be scattered. And we gave some estimates in previous lectures. We want, for example, a number of photons that is 10 to the 5, but can also be 10 to the 6 according to the scheme that you use. And so 10 to minus 4 is small, but not small enough. This means, for example, if you want to scatter 10 to the 5 photons, to decelerate an atom from room temperature velocity to basically the microkelvin region, so you see that in average, so this atom will absorb 10 photons to the wrong transition. And since from this transition the probability to go to the dark state, f equal 1, is on the order of 1, so you see that you might you can lose many atoms. So this is why laser cooling does not work, even if you have chosen the right transition, because of this pumping process due to non-resonant excitation of other hyperfine states. There is, however, a way to do that, to solve this problem, and the way to solve this problem is to use one additional laser. And in most of laser cooling experiments with alkali atoms, you use two different lasers. One cooling laser that is resonant or quasi-resonant on the transition 2 to 3, that is the right one, the closed transition that allows to have a good laser cooling, but then a repamper transition. So this is an additional laser that you need to put, that has the only purpose of taking the atoms that accidentally have arrived to this state because of decay from the f equal 2 state. So again, the cooling laser will excite to the f prime equal 3, but there is some small probability of excitation to f prime equal 2. From this state, atoms can decay to the f equal 1 state, so this will be a dark state. So you add this additional repumping laser, and the only purpose of this laser is to remove atoms from this state. So these atoms will be put back in the cycle. So they are excited to this state, but from this state they can also decay again to the f equal 2 state, and from that state they can participate again to the cooling process. So you see that when one deals with real-world atoms, so a lot of details have to be considered. And in particular, I can, when our labs will be open again, hopefully soon, so you might go in one of the labs working with rubidium or with lithium or with potassium, and you can ask the guys in the lab to block this repamper beam, and you will see that you will have 0 atoms in your optical molasses. So you need this extra laser to make this cooling transition a real close transition, so to prevent any possible decay to dark states that you want to remove at a level of at least 10 to minus 5, because these are the numbers that we need. Okay, so with this last part, with very experimental details, so I conclude. That's all for now. So see you for the next part of this lecture in the next video. Bye-bye.